Hey y'all, we are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be continuing our differential equation unit for the AP exam and we're going to be talking about exponential growth and decay, which does include half-lives. So keep in mind that this topic isn't that important in terms of how much it's covered on the AP exam. Perhaps it's only one multiple choice question on the calculator section. We would like to remind you that the biggest portion by far for differential equation free response questions is separate and integrate. So go check out our separate and integrate video if you want to cover a more bigger topic on the AP exam. But we still want to get every single question right. So we are going to be talking about exponential growth and decay. And what we're going to see is that it's going to be the same formula every single time. Maybe a formula you might be familiar with from a previous math or science course. So let's get started. Let's do exponential growth and decay. So exponential growth and decay. So there are very certain types of differential equations that are exponential growth questions, and those look of the form dy over dt is equal to k times y. So the wording of these questions is the following. What we're going to do is we're going to have a rate, so keeping in mind that dy dt is the rate. This rate is proportional, so it's k times something, and it's proportional to what? It's the population size. So it's k times the population size, which is y. So rate is proportional to population size. So those are the words that sort of tell you this is an exponential growth question, other than, of course, exponential growth itself, or maybe half-lives or something like that. And what happens is if you do a separate and integrate on this differential equation here, and you do our A way, again, we talked about this in our separate and integrate video, what you're going to get is you're going to get the equation that we're going to use today. And that equation is going to be P of t equals A E K T. So again, how you would do it is you would divide by y, you would separate, you would bring the dt over, you would take the integral. On one side, you would have the ln of y, that's the ln of y case that we talked a lot about in our separate and integrate video, so that what we do is we change it to a big A and so on. But in this video, when you're doing exponential growth questions, you can just skip to this formula. So we're not going to really care about the differential equation. We're going to be looking at this formula, and perhaps this formula is familiar with you because this is PERT in maybe a chemistry class. So AEKT or PERT. We're going to use A's and K's because K is in terms of proportional, and A is again because of that separate and integrate. But you can use basically any variable you want. So when we do these when we do these exponential growth and decay questions, notice we're going to first be solving for two things. We're going to be solving for A. A is very easy. A is going to be the initial. Secondly, we're going to be solving for this variable K, this constant K. And how we're going to do that is we're probably going to have another population. So that's going to be our goal today. So what we're going to do is first, we're going to be focusing on throughout the entire video, this equation right here, and we're going to be solving for this A and this K. And then once we have the formula, we might do something else beyond that. So just keep in mind that, again, we're just going to be covering this. Another thing before we do these examples is that this is really calculator heavy, but I don't have a calculator with me. So what I'm going to do is I'm going to write the answer, and the answers are going to be pretty convoluted. They're going to involve ln's and things like that. But if you wanted to find the actual answer, you would just type it in a calculator. So let's get started. So just throughout this question, we're going to be doing exponential growth questions. So perhaps there'll be more wording in the questions that would again have those words that the rate is proportional to the size of the population, the growth rate. So let's say we have one of those populations, so we do have exponential growth. And let's say we have a few values. Let's say we have population at t is equal to 0. Let's say it's just 100. And then let's say our population at t is equal to, let's say 2, meaning like 2 years or something, is 300. And finally, what the question, it's going to be a 3-part question. So let's see if we can do these 3 parts. The first part is just find an equation for the population at any time t. So this is the thing we're going to be focusing on, P equals AEKT. So find an equation for the population at any time. Then we're going to do the next simple question. So if we have question 1, step number 2 will be just a 1-second question, which is find the population at t is equal to 5. So all we're going to do is just plug in 5 into the equation in number 1. The third one is a little bit trickier. What we're going to do is we're going to find the t such that the population is 1,000. So instead of plugging in a t, we're going to solve for a t. But first off, we do have to do the questions in order. Let's take question number 1. So for question number 1, it's going to be the big formula P of t equals AEKT. So I always start off with that. P of t equals AEKT. And then we have 2 givens, and we're going to try to use those 2 givens to find A and to find K. So the first thing is to find A. A is always the initial time. Notice when you plug in 0, you're going to get e to the 0, which is 1. So A is always just the first time, the initial time, not initial time, but initial population. So in this case, A is going to be 100. Usually you can just eyeball what the A is based off the given. The harder one to go for is K. So we're going to use the second point to find K. What we're going to do is we're going to plug in T for 2, and then we're going to plug in 300 on the other side because that's the population at 2. So it looks like we're going to get 300 equals, again, keep in mind we're solving for K, so we're not going to be able to plug in anything for K. So it's going to be 100 e to the 2K. So now I'm going to go for K. A big thing when you're doing these questions is the following hint. You only can E and ln, or you can only ln and E if you want to reverse them, if they're inverse properties. So what we need to do is I like to isolate the E before I ln it. So what I tell my students is you can only ln an E if you want to get rid of the ln of E. So in this case, just one small step, we're going to divide by the 100 so that the E is isolated by itself. So it's going to be 3 equals e to the 2k. And now that I have e by itself, now I can ln both sides. So when you ln both sides, of course on this side you're going to get ln of 3. So on this side, we're lning for a purpose. It's because the ln and the e cancel out, so you're left with whatever was in the original exponent. So in this case, it's just going to be 2k. This allows me to find k pretty easily. It's going to be k is equal to ln of 3 divided by 2. Now again, these questions are usually calculators, so if you wanted to right now, you could type this in a calculator, but I don't mind too much that it's ln of 3 over 2. So let's write the answer. So the answer to number 1 is going to be this formula where a and k are the things we found. So in this case, a was 100, e, and then what is k? K is this weird number, but we don't really care. It's going to be ln of 3 over 2 times t. So that's the first answer. Now the second question is also pretty easy. All we're going to do is find the population at t equals 5. That means just plug in 5 for your t variable. So p of 5 is equal to 100 times e to the ln of 3 divided by 2 times k. Sorry, not times k, times 5 because you plug in 5 for t. So it's times 5. This is just a number. If you wanted to find the population at this time, you would just plug in the number. So again, that second question is really easy once you have the first one. So the one that's a little bit harder is step 3, so let's try that. We want to find a t as opposed to plugging in a t. So in this case, the population that's given 1,000 will be on the other side. 1,000 equals 100 e to the ln of 3 over 2 times t. So again, we're trying to isolate a variable in the exponent of an e. So the main sort of steps that we're going to do is we're going to try to ln both sides to get rid of that e. But again, you can only ln an e, or you can only e an ln. So what we're going to do is we're going to divide by 100 just quickly. So if you divide by 100, you're just going to get 10 equals e to the ln of 3 divided by 2 times t. Now we can take the ln of both sides. So when you take the ln of both sides, the ln of 10 will be on this side. And then because we took the ln of both sides, we're only going to be left with the exponent. So it's going to be ln of 3 divided by 2 times t. Finally, how do you find t? Well, you're going to just have divide by this constant. You're going to have fractions within fractions. But again, usually these questions are calculators, so you can just type this in a calculator. And that's it. So we're going to be doing this 2 more times throughout this video. But hopefully you see that the process isn't too bad. So when you have the wording of this question, it's like the rate is proportional to the population size. So you know you're doing exponential growth. What you want to do immediately is you want to use this formula, which is called PERT, or I call it AEKT. And you're always solving for the 2 constants, A and K. A is very easy. It's always the initial amount. K is a little bit harder, but what you do is you're going to plug in 2 for t and this population, in this case 300, into your the variables here, and you're just going to solve for k. The main thing is that before you get rid of an e by lning, you want to isolate that e. So we divided by 100, we took the ln of both sides, we got k was this. So that allowed us to write the equation because we just replaced k with this fancy number. We put 100 in the front because that's what a was, and that was our nice formula. Using that formula, we were able to find the population at t equals 5. We just plug in 5 for t. That one isn't too bad. And even the harder question, find when the population has reached 1,000. That question also isn't bad. We used the formula. We divided by 100 first off because you can only e and ln, or only ln and e. And finally, we took the ln's to get rid of e and divided, and we ended up getting this fun little number right here. So let's do the same thing, but with half-lives instead. And you'll see that half-lives is pretty similar. So let's erase this. So in this case, we have half-lives. So suppose you have some sort of compound whose half-life is, let's say, 100 years. Let's say that this compound initially has, let's say, 500 grams. So the compound has initially 500 grams. What we're going to do initially, we're going to do the same 3 questions. We're first going to find the population. So step 1 is find the population formula. Or find an expression that gives you the population at any time t, if you want to be more fancy. The second thing is we're going to plug in a number, so we're going to find the population at t is equal to, let's say, 300 years. And then finally, we are going to try to find at what time has the compound decayed 30% or so. So let's try this question. So half-lives work the same way. Don't be intimidated by half-lives. It's the same process that we just did. So what I like to do is I like to start off with a formula. P of t is equal to A E K T. Looks like we have an initial. Our initial is going to be 500 grams because that's how much amount of stuff we started off with. So we can replace this A with 500. So it's going to be 500 e to the kt. So now we need to find t, and again, how you do that is use a second condition. Well, it doesn't look like we have a second condition, but we do know that the half-life is 100 years. So if you don't know from chemistry or biology, what a half-life means is that after the half-life sort of transpires, you're left with half of the population. So for example, while it's not written nicely as a point in the last question where it would just like when p is equal to 2, you get a number. In this case, we can still use the half-life to try to find k. So what are we going to plug in? Keep in mind that we plug in things for t because t is a time value, and half-lives are time values. Half-life is how long it takes for you to reduce to half of your population. So we're going to have 500. That's not going to be disturbed. We're going to have k because we need to solve for that, so that's not going to be disturbed. So what are we going to plug in for t? Again, you plug in your half-life. So we're going to plug in 100. Then we need to know how much of the population is around after 100 years. Again, in the previous question, they just straight up told me. I do have to figure it out, but it's not that bad. Again, what a half-life is it takes the entire population and reduces it by 50%. So what's going to be in this spot? It's going to be 250. So it's going to be 250. So then, now that we have plugged in our initial condition, it'll be the same exact thing as the previous question. We're just going to solve for k. So remember that 250 divided by 500 is 1/2. The reason why we're doing this is because we only want to isolate the e so that we can ln it correctly. Keeping in mind that actually you didn't even need to know the initial because in half-life questions you would have the initial amount and you would have half the amount. So when you divide it by 2, you'll get 1/2. But we're still going to work with it. So it's going to be e to the k times 100. How do you isolate the e? Or how do you isolate the exponent? You ln the e. I don't know what I'm saying anymore. So it's going to be ln of 1/2 equals k times 100. So it looks like my k value that I care about so much is 100 ln of 1/2. Hopefully you can see this in the nice little corner here. So now we have a formula for number 1. So it's going to be P of t. It's going to be your initial amount, 500. And then finally, it's going to be e to the 1 over 100 ln of 1 over 2. That's k, a weird little number, but hopefully you can read it. And then it's going to be times t. So that's the first question. Again, whatever you do, you always just find the a, that's usually given, and then you find your k value. So in this case, k was 1 over 100 ln of 1/2. If you wanted to, you could of course type this in a calculator. Same thing for the second question. If you wanted to find the population after 300 years, what you would do is you just plug in 300 for t. So it's going to be 500 times e to the 1 over 10, 1 over 100, I believe. Not 1 over 10. ln of 1/2 times 300. And again, this looks pretty complicated, but you would have a calculator and you would just type in this calculator, and that would give you the population at t is equal to 300 years. Finally, for step 3, what you would do is you would do the same thing as the other question. So instead of plugging in a t, we're actually going to be solving for a t, so it's a little bit trickier. So let's just write down the equation, 500 e to the 1 over 100 ln of 1/2. We're going to be solving for a t, so we don't want to plug in anything for t. So now what we have to think about is what should we plug in for the next question, or what's the population side? So these questions are worded a little bit trickily, I guess. Just keep in mind that one preposition could change this question totally. So in this question, it says, at what time has the compound decayed 30%? So remember that when you put in this population, you put the population at that time. So we want to find the population where it decayed 30%. So what we're going to put over here is not 30% of 500, we're going to put 70% of 500, because if it decayed 30%, then that would mean that would have 70% of 500. So in this case, it's going to be 0.7 times 500. Keep in mind that if we again added the preposition to, then this left side would be different. If I said instead, at what time has the compound decayed to 30%, that means we're trying to find the time where only 30% of the population is remaining. So we would put 0.3 times 500 on the left side. So again, on this left side, it's always whatever population you have, whatever time you're going for to have a desirable population. So in this case, our desired population was decayed 30%. That means 70% remains. So we're putting 70% on this side. Keep in mind that we don't need to do 0.7 times 500, because again, we're going to isolate this. So it's going to be 0.7 equals e to the 1 over 100 ln of 1/2 times t. Just like in the previous question, what you do is you take the ln of both sides. So you take the ln of both sides, that gets rid of the e on the other side, and then you just divide by this weird number and you're good to go. So you might have a calculator, so you don't have to write this all out. But in this case, it's not too bad. It's going to be the ln of 0.7 divided by this. 100 ln of 1/2 t. And that's how half-lives work. So it's the same thing as the previous question. It's the same formula, P of t equals AEKT. A is still the initial population. The only thing you have to think about is what the definition of half-life is. And a half-life is after the half-life happens, you remain half of the population. So in this case, when you want to plug in your second point for these half-life questions, just plug in the half-life for your t, and then for the other side, it'll be half the population. So in this case, what's half of the 500? It's 250. So t always goes into your half-life always goes in your t, because again, it's a t value. Once you have that, then the question is still the same as the previous one. You isolate the e, you take the ln on both sides, you solve for that k, and then question 2 is different than question 3 because we're plugging in a t. In question 3, we're solving for a t. And keep in mind that we found 70% remaining because it decayed 30%. So even these half-life questions are a little bit worded more challenging than the previous question, it's still the same steps, back to back to back, if you can know what half-lives are. But for the rest of the question, I'm going to do one more question just as a sort of feel, just to make sure that you sort of got this. So let's do that. So let me erase this. And we're not going to do 3 subparts because we sort of have an idea of what's going on. But let's say we have our normal situation. So we have a rate proportional to the growth, to the size of the population, the growth rate of the size of the population. So in this case, we're going to know that it takes a population let's say 20 years to double. So the question I'm going to try to ask, and this is the last one, is how many years does it take for the population to triple? How many years does it take for the population to triple? Keep in mind, of course, that we're dealing with exponential growth. So that would have had words in the beginning of this question. It would have had said something, again, like the growth rate is proportional to the size of the population. If that is true, and it takes the population 20 years to double, this is not a question mark, this is a period, how many years does it take for the population to triple instead? So let's start off with the formula. Again, you always start off with P of t is equal A, E, K, T. So now this one's a little bit weirder because we don't know what A is, but that's going to be fine. We're just going to leave it as A because we actually don't need to find A. So now we're going to go for this guy right here. So we're going to use our first initial condition just like normal. We don't have A, so let's just use the other condition and we might not even need to find A. So let's see what happens. So it says it takes the population 20 years to double. So just like with our half-life questions, you always plug in years into your T value. So I know what I'm going to plug in for T. That's going to be 20. So it's going to be A, E to the 20K because I'm plugging in T for 20. Again, I'm solving for K. Didn't have a chance to solve for A because there was no initial, but you actually don't need the A as you're going to see. So we actually just need the K. So we're going for K. We're plugging in this point. So the question is, what do we have on the other side? But this is why you don't need A. The other side is always the population after whatever time you plug in. Well, it takes the population 20 years to double. So what's on the other side of this equation? It's just going to be 2A. And notice that why we didn't need to know A in the first place, because these A's cancel pretty nicely. So you're going to have 2 is equal to E to the 20K. So you're always solving for these two variables, A and K, but sometimes you're not always solving, I guess. You're only solving for K. So now we're going to do our normal thing where we're going to take the ln of both sides because the E is already isolated. So it looks like ln of 2 equals 20K. So that means K is equal to ln of 2 over 20. So now what we do is we are going to write our formula. P of t, still don't know what A is, but it actually doesn't matter. So we're just going to write E to the ln of 2 over 20 times t. And now what we need is we need to find the question actually. So what you want to think about is, do I actually plug in a time or do I plug in a population and solve for a time? So in this case, it's going to be plugging in a population to find the time because we don't know how many years this takes. The answer is years, so we don't want to plug in anything for t. So what we're going to do is we're going to try to solve for a certain time. Still don't know A, but we don't need to know the initial population actually. We do want to plug something into the right side. So what does this t value represent? Well, this t value is for the population to triple. So what do we want on the other side? Well, when it doubled, we put 2A. When it tripled, we're going to put 3A. Because no matter what the population is, after we solve for this time value is for the population to triple. So you're going to have 3A on the other side. And notice that again, you don't need to know what A is because the A's immediately cancel. So you're going to be left with 3 equals E to the ln of 2 over 20. This was K times T. Finally, you're just going to solve for T one last time. Take the ln of both sides. It's going to be ln of 3 equals ln of 2 over 20t. So we can write the answer in this nice big box here. We're going to divide by our K value. It's going to be ln of 3 divided by ln of 2 over 20. And that's how you do exponential growth. So hopefully you see that these exponential growth questions aren't too bad. Again, all you do is use this beautiful formula, P of t equals AEKT. If they give you an initial condition, that's great, plug it in for A. But the main variable you're solving for, the main constant you're solving for, is this K right here. And how to do that is they always give you a second initial condition. So use that initial condition, keeping in mind that you always plug in years or days or whatever into time, including half-lives, and you're going to set it equal to whatever the population is at that time. They might give it to you. It might be in terms of your initial. So in this case, it was 2A. Then you go for the K. Remember that you need to isolate the E before you ln it. But once you isolate it, you can ln it and you only get the exponential because E and ln are inverses. That will give you the K. and then you replace the k with whatever it is. You could have typed this in a calculator if you needed to. So you get this formula right here. And then the next questions are usually plug in a time. That's very easy. You just replace the t with that number. Or solve for a time, which is slightly harder, but not too much harder. What you do is you're given a certain population. You cancel things out just like normal. Isolate that e, ln both sides, and you'll be able to solve for every time value you want. So while exponential growth and decay isn't the biggest question, it isn't the hardest thing in the world, but we still want to get questions right, certainly. And this does appear in other classes, actually, other science classes like environmental science or chemistry or something like that. So if you want more practice with these questions, you can certainly watch our Girls Teach Calculus video. I'll link that in the description below, where one of my former students practices a lot of exponential growth and decay questions. She uses this formula basically in every single question, of course. She does half-life questions. She finds certain populations at times, and then she finds certain times for certain populations after she solves for her variables a and k. But thanks again for watching Just Like Normal. If you continue on with our series, we might have a few BC videos next in our playlist where we talk about logistic growth, which is a different kind of growth than exponential growth. So be on the lookout for that. Thanks again for watching Just Like Normal, and I hope to see you then. Thanks again.